So hi everyone. We are going to talk in these lectures about Bayesian nonparametrics. So the purpose of these lectures is twofold. So first, one goal is to introduce a set of tools that have been developed in maybe the last 20, 25 years to study Bayesian posterior distributions. And the second goal is to present a few recent contributions, a few more recent things that people have been considering, in particular in specific models, either high dimensions or deep neural networks. We're going to talk also a little bit about variational methods. Okay, so I'm going to define a little bit today in the first lecture the words in the title. So the first lecture will be an introduction and about rates of convergence, so I'll call that rates 1. Okay, so we are going to start with a statistical model. So it is just a collection of probability measures on some space X, indexed by some set of parameters. Okay, so here we have probability measures. I'm going to give a few examples, of course, in a second. So here theta is a set of parameters. Okay, and we're going to, as statisticians, we observe some data. So the data I'm going to denote by X. So in fact, rather xn, because n will be some quantity quantifying the number, typically either a number of observation or a certain signal-to-noise ratio. And often I'll even drop the notation, the dependence in n. Okay, so that's observations. And for now, you can think of it as xn drawn according to one of these measures, p theta n. Okay, so I say for now because in a bit we are going to change a little bit the rule of the games, but first we can think of it as this. All right, and so what about nonparametrics? So in nonparametrics, so I'm not going to define it precisely, but essentially anything that is not a parameter in finite dimensions. So the basic example is when you want to estimate a function, okay? But it can be a pair of a parameter, a real parameter and a function. It could be a matrix. It can be with growing dimension, for instance, okay? So for me, it will be anything that doesn't really fall into the classical parametric setting. So, but just to fix ideas, think of, for instance, theta equals to f, a function. Okay. So a few examples. So maybe the kind of the classical example is nonparametric regression. So in this case, the data is just you observe some points, so maybe on the interval 0, 1. Okay, so you have somewhere in the background you have an unknown function f that you don't observe, and you just observe it. You observe noisy versions of it at certain data points. So a very simple version of the model is the fixed design nonparametric regression. Okay. where x here is just the x1, xn. And here I'm going to write p. So pfn is just product measure of. So if, for instance, I assume that epsilon i's are IAD standard normal, so Gaussian regression, I get f of at the point of design and with variance 1. Okay? So that's one simple example. In fact, it's maybe not the easiest technically to study because then you have these discrete design points. You'll get things like certain sums of observations of f at the data points that approximate, say, the integral. So it's actually easier to work with a continuous version of that. Gaussian white noise model. Okay, so a canonical way to write this is, it's again a signal plus noise model. Okay, this. And there will be two different ways that in statistics we interpret it. So what do we observe? So we have two observational schemes. So one is just that we observe the path xn of x. So that's the integral. So I just integrate this from 0 to x, okay, plus wx over square root n. And here I have, generally we take Brownian motion. Okay, so here I get Brownian motion. And here I have some L2, so f belongs to L2. Okay. So that's one possibility, and maybe one that is even more used in statistics is just one where here so suppose, so you know, a bit like in physics, like if I have a basis, like a Fourier basis or a wavelet basis, I can just project this thing onto the basis and then just assume that actually I observe the collection of the projections. Okay, so when I write this, I get something which can be written this way. So once I've written it, I can actually forget about this. I can just say, assume that I observe this. Okay, so x here is the sequence of xk's, and now little fk is a sequence in little L2, and epsilon k's are just IID and 0, 1. Okay? So in both cases, we can, I'll not write it here because it's kind of the first board, but you can also write the distribution. Okay, I'll come back to it a bit later in the course. And maybe give a last third example, which is maybe the first that is often given, which is density estimation. But in a sense, it's maybe, so all those are very basic nonparametric models. It's kind of the basic trilogy of models. But technically, maybe the last one is slightly more involved because you have some normalization with the density. Okay, so it's not here. The function f can take negative values. Okay, whereas here it will be a bit more constrained. So density estimation is very easy. You have x1, xn, observe IID from a certain distribution with density f on 0, 1. Okay, so here what we observe is you observe some points. Okay, so suppose we have a draw from a density F. So maybe I have a lot of observations here and here. So if I observe this, maybe I can think that probably in the background I have something which is, I don't know, something like this maybe, okay? And of course, as a statistician, I only observe the red crosses, and I'd like to reconstruct this background density F, okay? And so F is a density, so it's positive and it integrates to 1, okay? And so that's density estimation on 0, 1, but then we could think of density estimations on other spaces. For instance, if I think of a sphere, I can imagine that I have some data on the sphere, okay, density estimation on the sphere M or on a manifold, or okay. So that's also an interesting statistical model we'll discuss a bit later in the lectures. Okay, so I don't know if there are questions while I erase. So now what about Bayesian in Bayesian nonparametrics? Okay, so we have our theta model, and theta is unknown typically to the statistician. Okay. So what do we do? So the Bayesian kind of paradigm is to say, which comes dates back to Thomas Bayes, but also Laplace was a great promoter of these Bayesian ideas, maybe in some thing that is called inverse probability. So in the Bayesian paradigm, what you say is, okay, I don't know theta, I'll just suppose it's random, okay? So in a sense, make theta random. So in a sense, Bayesian statistics is kind of very probabilistic in a way, in the sense that everything is random, okay? So how do we formalize this? So we'll have two steps. So the first step is just make theta random, okay? So I'm going to assume that theta is drawn from pi. Well, actually, I can choose pi, so it's called prior measure or prior distribution on capital theta. Okay, so it's just a probability distribution on capital theta that you give yourself, that you choose. Okay. So the step 1 bis, say, is okay. So, but then if we do that, so what do we do with p theta? So we view now p theta n as the law of xn given theta, because now theta is random. Okay, so when you do this, you give yourself a marginal distribution for theta, and this conditional, so, or in other terms, it's equivalent to what you have just done, is you have given a certain distribution to the pair, so that gives the Bayesian law of the pair x theta. Okay, so in particular, in the Bayesian world, the law of xn is not a p theta. Okay, it's a mixture of p thetas. So that's why before I said that. Okay, so xn is drawn from this is more what's called the frequentist assumption. Okay, so in the Bayesian setting, you have a law for you give yourself a law on the parameter, on the unknown parameter, and then you view the laws in the model as the conditional distribution of the data given the parameter, okay? Because then you fix the parameter, p theta is this distribution once you give me the parameter, okay? And now, once I have a law on the pair, I can just form the other conditional, okay, which is the conditional distribution now of theta given x, and that is the Bayesian estimator, which is called the posterior distribution. Okay, so step two is going to be, I take theta given xn, the other conditional is what's called the posterior distribution. And that is the object we're going to work with, this conditional distribution of theta given the data, okay? And we denote it, it's going to be denoted p dot, so it's a distribution, okay? And I denoted p dot given x. Okay, you notice that I already dropped the index n in the notation, but it's always there. Okay, so the interpretation is that, in a sense, so you have some prior, maybe reflecting some prior knowledge that you have about your experiment, which you encode in the prior, in this distribution. And this gets updated with the data by this conditioning operation, okay? So the prior gets updated once you see the observation, okay? To form the posterior. Okay? So now one important assumption the next step now is to say, okay, how are we going to work on this posterior distribution? So either you assume nothing and then you have just some conditional distribution. But here in these lectures, I'm going to consider the framework where there will be a base formula. So to have a base formula, you need some condition, some domination condition. Okay. So assume that, so it's a classical assumption, but actually there is a whole part of Bayesian statistics which doesn't assume this, and it's also very interesting. For instance, when you work with discrete probability measures that have atoms that are random, then you don't have a dominating measure, and that's also, there are a lot of interesting works in that area as well. But here I'm going to assume that all p theta n are absolutely continuous with respect to some fixed, to a fixed mu n. Okay, so dp theta is equal to small p theta. So hopefully my small p and the big P will be distinguishable. Otherwise, please protest. Okay, so I have some fixed dominating measure for all theta, in capital theta. Okay. All right. So, for instance, in the first model that I erased here already, in the regression model, you could just take a Lebesgue measure on Rn. Okay. So that's an important assumption, which is going to allow us to write down a base formula. Okay, and sometimes, so just in brackets, well, sometimes there is also a natural dominating measure on capital theta. So sometimes I'll just write this, so little pi then will be the density with respect to nu. So that's if nu is a dominating measure on capital theta. Okay, but often I will just take nu equals pi, capital pi, and then small pi is equal to 1. All right, and so that's one part, and then just measurability assumption so that you can write down the base formula. So this is, we are going to assume that it's measurable. And under those conditions, you can write down the conditional density of theta given x. And that's the object we are going to be working on in the lectures. Okay, so maybe it's good that I have this blackboard because then it can stay here. Okay. So under those conditions, we have a base formula. Okay. So base formula tells us that the posterior distribution has density. So theta gives p small t theta and x, p theta divided by integral. Okay, so that's just the usual small t theta d, okay, with respect to u. Okay, so that's base formula. So that's the usual formula for the conditional density. So maybe just the first kind of fundamental basic example is a very important example, actually, even if it's maybe the simplest one, but say you can understand already a lot in statistics just with this very simple model. So that's just a Gaussian shift experiment where a translation model where you want to estimate, you have Gaussian observations and you want to estimate the location parameter. Okay, so that's very classical. So what if you want to take the Bayesian approach, you can, for instance, what's natural here is to take, so you have to take a prior distribution on theta. Here it's quite natural to take just a Gaussian one because it makes computation simple here. It's what one called conjugate. Okay, so here again, so the observations are just a sample, x1, xn. So they're in the Bayesian model, the distribution given the parameter is just the IID and theta 1. Okay, and then if you apply this formula, you get quite immediately that the posterior distribution is a Gaussian centered near the sample average, x bar, and with variance 1 over n plus 1. Okay? So that's a distribution that depends on the data, okay, and on n. Right? So in particular, so compared to more maybe straightforward estimators here, x bar is kind of canonical here. So what you get extra with the Bayesian approach is that you get some distribution. Okay, so you don't get only x bar, you get something. So here I have what can be the posterior mean here, which is very close to x bar, and x bar over n plus 1. Okay, so x bar is maybe here. And I have some spread also in the, so I have 1 over n plus 1 variance, so it's roughly here something of the order 1 over square root n. Okay? And the fact that I not only have a location but also a spread is something that is maybe interesting to do what's called uncertainty quantification. And uncertainty quantification just means that you want to, well, as the name indicates, quantify the uncertainty that is present about the parameter. So not only have a point estimate, but say something about, okay, what is the probability that I'm close or not to this parameter, how big is a region of high probability under which the parameter is in this region. Okay, so from the Bayesian perspective, so the posterior can be used, maybe, I don't know, for uncertainty quantification. Okay, so that's one main motivation. On using Bayes, I'm going to give a few examples now. But before that, let me just give a definition. So from the Bayesian perspective, what we call a credible set, a measurable set included in theta, which may depend on the data. So credible set, what it is just a set of large probability under the posterior. Okay, so a credible set of level exactly 1 minus alpha is a set which gets 1 minus alpha or at least 1 minus alpha probability. So here you may take something, a quantile set, for instance. So you have your Gaussian, you just take 0.05 and 0.95 quantiles, and then you get this interval that depends on the data that's around your posterior mean. Okay, so that's just a definition. So let me give maybe as a motivation questions so far. Okay. So just as a practical motivation, so the practical use of Bayesian method, so it's very widespread in application. Let me just discuss, so in the notes I've put I think 3 or 4, let me just talk briefly about 2 of them. So one of them is inverse problems and practical inverse problems, for instance in medical imaging. So you have several situations where you want to do a tomography. So it's an inverse problem. So you have, for instance, the positon emission tomography, which is something in medical imaging where a patient gets injected some liquid with a bit of radioactivity in it, and then for instance if you do a PET scan of the brain, after a certain time you will have some inside the brain you will have some emissions, and of course we cannot register inside the brain, so typically you look at the outside, so you want to reconstruct the signal inside from the measurements on the outside. Okay, so that's a typical inverse problem. You also have electrical impedance tomography, for instance, where now it's a different experiment where you a different medical imaging technique where you register, you put some electrodes on the body and then you put some electric signal and you look at what comes out. Okay. And so in this situation, so in medical like devices, Bayesian methods and Bayesian nonparametric methods are used to produce, so not only point estimators but also uncertainty quantification, like this region, okay, may belong to this or has this intensity, but I also have some degree of knowledge of whether I'm very confident. So if this region is very thin, I'm very confident. If it's broader, I'm less confident. Okay. And also, so in many areas, also in astrostatistics, in astrophysics, so you have maybe many of you have heard about this gravitational waves detection. So a few years ago, gravitational waves were detected, and if you look at the paper, you have a lot of Bayesian methodology used, and in particular, they have these specific signals of the waves, and one way they showed that they were quite sure that this signal occurred is that they had some credible bands here around this, and said, okay, it's a characteristic form I expect. Okay, and also a few days ago, you may have heard in the news that they also detected some gravitational wave background, and there again they use quite a bit of Bayesian technology. So both Gaussian series priors that we are going to see in a few see pop up in a few lectures, and also Bayesian testing, which we'll talk about in chapter 7 of the lecture. So there are many other examples, but just as a little motivation. Okay, and if you are in a nonparametric context, what you so when you estimate a function, so what we'll do in a moment is that you have a random, you have to draw the function at random, and your posterior distribution is a distribution over functions. Okay, so what people do often in practice is that if you know how to sample from your posterior, then you get you can draw many times from them. So they are random, so you don't get the same function. But if you draw them many times, you get a sort of what's called maybe sometimes a spaghetti plot with all these plots, and then you can have maybe, if you take the envelopes, or maybe 95%, if you find a band where 95% of the curves are in, that reflects some Bayesian uncertainty about it. Okay, so we will go a bit in that direction in a moment. All right, so if we are going to do that in the nonparametric settings, we have to talk about priors on functions. So for people doing probability theory, I think it's very natural to have prior on functions, right? So say Brownian motion, all right, as a canonical example. So as soon as you have a stochastic process with which has maybe continuous sample paths, for instance. Okay. So for instance, Gaussian processes. So you may use the distribution they induce on continuous functions to as a prior distribution. Okay. So for instance, Brownian motion. Okay, say, called it WT before, but let's call it BT now. Then you have, right, a path of Brownian motion is something like this. Okay, then you may start thinking, okay, is it a good model for functions? Where probably in a sense, but maybe it helps also taking different Gaussian processes. Maybe the behavior will be different, and actually it will be, as we'll see tomorrow, I think. So you can just take your favorite stochastic process here and use it as a prior distribution. Okay, I mean, in any of these problems I took before. So you can, so here Brownian motion, so you have, it's centered, and you get a covariance which is S in t, the minimum of S and t. You could take integrated Brownian motion if you want something slightly smoother. Okay, you can also take, so more generally, you can take a fractional integral of it. So that's called the Riemann-Liouville process. I mean, it's not very important. It's just given, since it arises often in the literature, I'm just giving it. Okay, so that's called the Riemann-Liouville process. So for alpha equals to a half, you get Brownian motion. Alpha 3/2, you get integrated Brownian motion. And otherwise, you get a sort of an alpha regular. So that's called the Riemann-Liouville process. Okay, so that's another Gaussian process. And let me, by the way, mention that, so because it will be important in the sequel, is that Brownian motion, in a sense, it has, so you can show that it has a version with path as is c half minus epsilon. So it's older half minus epsilon for any epsilon. So in a certain sense, it's a half regular. Okay, and this process here, in a certain sense, is alpha regular. Okay, so you can have even more regular processes. So you can have a process which is very popular in machine learning. It's a squared exponential Gaussian process whose covariance structure is just an exponential. So it's a much smoother function. And in fact, the paths that you get are analytic. So you get something which is very smooth like this. Okay, so a different behavior. So you could also consider maybe in the spirit of this Gaussian sequence model, so this projection of white noise onto a basis, you have something natural as a prior is a series prior, which these priors are going to be important also in the sequel. And a series prior is just you take a random a function with random coefficients into a basis. Okay, so if you think about the Fourier basis, it will be a random Fourier function. Okay, so you have typically, you give yourself a basis Ek of an orthonormal basis of L2, and then you put here some IID variables, for instance, IID n0, 1, or it could be something else. And here you put sigma k is some sequence, say, in L2. Okay, so that draws, again, a function at random. Okay, so if you want to use this in this density estimation setting, you have to be a bit careful because you cannot use that directly as a prior because you have, well, I already erased it, but in the density setting, you have, so recall, for density estimation, you had this constraint, okay, f positive and integral of f is equal to 1. So you cannot directly use Brownian motion, but you could use something like a renormalized Brownian motion. Okay, so you could put it in or any of these processes, you could put it in an exponential and renormalize. Okay, and then you get a random density. Okay, there are other ways to do, many other ways to build random densities, some of which we'll discuss also later. Okay, so any questions at this point? Okay. So if not, we are going to now, I'm going to talk about what rate will mean. So what about convergence of posteriors? Okay. So now it's an important part where we are going to specify what we mean by studying the posterior distribution mathematically. Okay, so convergence of posterior distributions. Okay, so recall that I have my model here, which is dominated, and I have a prior theta, pi, sorry, on capital pi on theta. Right, so the Bayesian setting is saying I put a prior on pi on theta, and I view the distribution of the data given theta as the distribution in my model. Okay, so this is the Bayesian setting. Okay. Which I can call maybe B. Okay. And from this, I deduce this the other conditional, the conditional theta given x, okay, which is the posterior. So here there are various options to study this. Okay, so by this here, by the base formula, I know that I can express. So let me write it again. So now I'll remove the little pi. I'll write directly in terms of capital pi. So integral of p theta of x d capital pi of theta, integral over b, divided by the normalizing constant. Okay, so to express the convergence, I have maybe two options. So option one would be, so we are not the one we are not going to take, would be to study it in the purely Bayesian model, in the Bayesian setting B. Okay, so that's done in what's called decision theory, in particular. So it is helpful, and also I guess purely Bayesians also may want to consider only this framework. So the drawback, the problem of this framework is that it's a bit subjective. So it's interesting, but it's prior dependent. In principle, it's prior dependent. So two statisticians taking two different priors, well, typically get different answers. So of course, then you may perhaps want to study also, it's interesting to, the posteriors may merge in the sense that, in fact, when n goes to infinity, the posteriors resemble. You can consider this type of questions. But from the optimality perspective, for instance, you get here things like, you may recall from classical statistics courses that, for instance, in this Bayesian setting, you know that the posterior mean, for instance, is an optimal estimator for the quadratic risk. Okay, but then this notion of optimality completely depends on the prior. Okay, so if you take a different prior, you get a different optimal estimator. So here we are going to take a different perspective, which is called the frequentist analysis of posterior distributions. So that's what we are going to follow here in the lectures. We'll go back occasionally to this. This can be helpful. Also, if you do option 2. So we do what's called frequentist analysis. So that's important because that's what we are going to use this setting in all what follows. So what's the frequentist analysis? It's just that you use the Bayesian framework to produce this data-dependent probability distribution, the posterior given the data. And here we're going to assume that there actually exists a theta 0 in capital theta. So we make the usual assumption of statistics, true parameter such that so x is generated from p theta 0 n. Okay, so we are not in the Bayesian framework because in the Bayesian framework p theta 0 would be the law of x given theta equals theta 0. But we just use the Bayesian framework to produce this object, which after all is just a certain function of the observation. So it's a generalized estimator. And then we will ask the usual question in statistics. Suppose there is a true, the data has actually been generated from a certain true parameter, and study. Then we study pi dot given x in probability under p theta naught n. Okay, so this means that I study this object in probability under p theta naught. Okay, so in this basic example, it just means that I have this distribution, and I study it under the assumption that x1, xn are IID and theta naught 1. Okay. And in this setting, x bar will converge to theta naught, okay? And we can say many things about this. Okay, so that's the main setting we'll consider. Okay, and given that, I can now define what the concentration rate is. Yes?
When you mentioned the application before,
Yeah.
in the application, do they assume that we are in option 2 or in option 1? How do they model the data?
So that's a good question. So for instance, in the gravitational wave experiment, they actually checked, there is a part of the paper where they say, let's try to check this under a vanilla model where there is a true theta naught. And they were, they actually checked that it has the credible set they consider has the good frequentist property. So they also consider the frequentist setting, okay? So that, I mean, it may depend a little bit on the example that they have in mind, but they do a frequentist analysis, yeah, sure. So in this setting, actually, they didn't prove the mathematical result, but they checked it in practice that the credibility, so the frequentist coverage of the set goes to the expected coverage, actually. So it's a frequentist result. Other questions? So contraction rate. So we say that epsilon n is a contraction rate. So it's a rate for pi dot given x, okay, around theta 0 with respect to a distance d to a distance d on capital theta if well, so let me maybe do a picture before. So if you look at a ball in terms of the distance d around theta 0 of radius epsilon n, all the mass of the posterior asymptotically is inside this ball. Okay? So let me just write it as a statement. So the ball of radius, so how did I write it? With the complement, but given the data. Okay, so that goes to 0. So in probability under p theta naught as n goes to infinity. Okay, so here I just wrote that the mass, the complement of the ball of radius epsilon n goes to 0 as n goes to infinity. Okay? So in the basic example over there, it's easy to check that any sequence of the type mn divided by square root n, where capital Mn goes to infinity, that's going to be a rate for this posterior distribution. Okay, and for actually many priors, you'll get the same behavior, and the rate will be essentially 1 over square root n up to this slowly any diverging factor. And that's a kind of characteristic of parametric models. Okay. So now we are going to start. So the goal now is in nonparametrics, we want to study this object where typically theta is maybe a function. Okay, so now in the remaining of the lecture today, I'm going to introduce some tools to study this. Okay, so one important quantity that emerges is a Kullback-Leibler neighborhood. of theta 0. So let me recall that if you have two probability measures P and Q, the Kullback-Leibler divergence is given as follows. And we are going also to need a V, which is just, can view as the variance of this. Okay. So dP over dq, you recenter by the Kullback-Leibler, I put a square dq. Okay, so it's sort of a variance of the KL. And we are going to define now a Kullback-Leibler neighborhood as bk, k for Kullback, theta naught epsilon. So that's the set of thetas such that k p theta naught p theta smaller than n epsilon squared, and v p theta naught p theta is smaller than n epsilon squared. So here I can put, n here, but as I said, I often drop the dependence, but in all examples, everything depends on n, okay? So that's why I also have an n here. All right, so that's a certain neighborhood of theta 0. It's a set of thetas such that these divergences are renormalized by n, say, are smaller than epsilon squared. Okay. So that's going to appear in many proofs, and the reason why it's important is because it is going to help us bounding from below the denominator of the base formula. Okay, so I'm going to state first lemma. So today we are going to state a result due to Gosal-Gosch and Vernevart. And so it's a generic theorem that gives you a certain rate of convergence for posteriors. And I'm giving really the simplest versions. There are a lot of variants and refinements, but I'm giving really the simplest one, which is already very helpful. Okay, and so this was established a bit over 20 years ago, and there's been a lot of activity in trying to understand how to apply it and going beyond that recently. Okay, so first lemma will be about, so if we want to study the Bayesian posterior distribution, we are going to need to do something about the denominator. Okay, so here, as I said before, so here I write with respect to pi, and so I take small pi equals to 1 d pi. And before I'm writing the lemma, just a little remark that I could have made before is that note that in the dominated setting, the posterior distribution is dominated by the prior. So in particular, if you have a set B on which you don't put any mass, okay, if pi of B is 0, then pi of B given x is also 0. Okay? So that's kind of straightforward, but we are going to see a more quantitative version of it. And so if you want to, if your posterior, if you want it to be good at convergence, you are going to need to put some mass around the point you want to converge to. But I'll go back to that in a second. Okay, so first lemma is, let's try to bound the denominator from below. So let's P probability, so prior on capital theta. And let's take two positive constants, C and epsilon. So with P theta 0 probability at least 1 minus C squared n epsilon squared minus 1, the integral of P theta. So one thing also I'm going to do. here is that notice that I can divide up and down by p. So all these are small p's, no? The densities. I can divide up and down by small p of theta naught. And I can do that because anyways I'm studying this object in probability under p theta naught. So even if this is 0, so I can drop the sets on which this is 0. Okay? And this I can do because it doesn't depend on theta, up and down. Okay? So it's a constant with respect to theta. So I divide up and down by the same guy, but at p theta 0. Okay? All right, and the reason I do that is because I study the behavior in probability under p theta naught, so it will be helpful to have this normalization. We'll see it in a second. So p theta divided by p theta naught, small ones, okay, the densities. Okay, so I can also write it like this, so it's clear that it's a small p. Okay, d pi of theta. This is going to be bounded from below by pi the prior mass of the neighborhood of theta naught times e to the minus 1 plus c and epsilon squared. Okay, so let's prove this. So let B denote this neighborhood. Okay, and let's introduce, so pi bar will just be the normalization of pi to B. Okay, so I assume that pi of B is non-zero, otherwise it's trivial. Okay, so pi bar is now a probability measure on B. And so here, let's say that this is the D-like denominator. So the denominator is bounded from below by, certainly I just integrate on B, so I make it, if I do that, I just make the integral smaller. Okay, and then I can just say that this is equal to pi bar, to pi of B, and the integral just by definition of pi bar. Okay, p theta over p theta naught of x, d pi bar of theta. Okay, and now what's nice with pi bar is that I can use Jensen's inequality. Okay, so by Jensen, I know that the logarithm of p theta over p theta naught of x d pi of theta, this is larger than the integral of the logarithm p theta over p theta naught of x, d pi bar of theta. Okay, so now to kind of link, here we start seeing appearing something a bit related to the Kullback library, but with a different sign, right? I have log p theta over p theta naught, so let me flip the sign. Okay, so if I can certainly write this as the integral of minus, so the integral of log p theta over p theta naught of x, I flipped the sign, I said. Okay, and here I am going to subtract the KL. Okay. D pi bar of theta, but so if I subtract the KL, I have to, and with the minus, I have to remove it. So with the integral, so minus the integral of k theta naught theta d pi bar of theta. Okay, but now this term, note that since I'm on pi restricted to B. On B, by definition, the KL is smaller than n epsilon n squared. Okay, so this is going to be bigger than minus n epsilon n squared. All right, and now let me focus on the first quantity over there. This one. So this is a random variable, okay, because it depends on x, which I'll call z. And let me study it. Okay, so recall that I want to bound the denominator from below, so I want to find a set of high probability such that this is bounded from below. Okay, so here what I have is at the minus z minus n epsilon squared for now. So define Bn to be the event on which z is in absolute value smaller than Cn epsilon squared. Okay, and we are going to show that it is an event of high probability. Okay, so first notice that, so the reason I subtracted k is to make this centered, because now if I take the expectation and the theta naught, I can do Fubini, right? So if I do Fubini, I put the E theta naught inside, and I get exactly this guy, okay? So which is the centering, right? So this is 0 by Fubini. All right? And then I can also control the variance. So E theta naught of z square. So if I have a square, I can do Jensen again with the square and say that this is smaller than E theta naught of the integral of log p theta over p theta naught of x minus the Kullback-Leibler squared. So now I've put the squared inside. Okay, and now I do Fubini again. I put the expectation inside, and I get exactly v. All right, so I get the integral of v p theta 0 d pi bar of theta. But as pi bar is probability distribution on B, and on B I control V by n epsilon squared, I know that this is smaller than n epsilon squared. Okay? Great. So now I'll just do Chebyshev, okay, to control the probability of the complement of this event. So very simple, okay, so we use just the very basic tools here, Jensen, Fubini, and Chebyshev. So hard to make it much simpler. So we probability of Bn complement, okay, just by Chebyshev is smaller than E theta naught z squared divided by Cn epsilon n squared, and this, so we get, so this is, we have bounded by n epsilon n squared, so you get 1 over c squared n epsilon n squared. Okay? And now we just look at what we proved. So on this event Bn now, we have that here we just proved that on Bn, so d is larger than pi of b, exponential, because I have something on the log here, exponential of minus c n epsilon squared minus n epsilon squared. Okay, 1 n epsilon squared comes from here, and the c comes from the z. Okay, and so that gives the result. Okay. Okay, so simple lemma to control the denominator. And now we'll state a second lemma. Shall we here maybe. Which is going to be a quantitative version of this very simple statement. So let me keep this just as a reminder. So lemma 2 is going to say the following. So suppose I have some an measurable sets and epsilon n with such that n epsilon n squared goes to infinity. Suppose that a certain ratio, so pi of an divided by e minus 2n epsilon n squared, pi of my KL neighborhood of before, of size epsilon n. So suppose that this goes to 0 in probability. No, sorry, this goes to 0, it's not random, as n goes to infinity. Okay, then e theta 0 pi of an given x is a little o of 1. Okay, so this is a very helpful lemma which tells you that so this condition says that pi of an has to be a little o of this guy at the denominator, and it has an exponential in it, so it has to be very small. So it says that if a set or sequence of sets gets very small prior mass, then its posterior distribution vanishes. Okay, so it kind of makes this quantitative. And it's very helpful because it allows you to exclude some sets you don't want to work with or difficult parts of the parameter set. If the prior doesn't put a lot of mass on them, then the posterior neither. Okay. So the proof is quite simple. Let's start it here. So the proof of lemma 2 is just as follows. So the pi an of x. So let's write it as before with this little trick that I renormalize by p theta naught. Okay, d pi of theta divided by the integral of the same thing. And here I say either I'm on the set, so En will be this event. Okay. So what is En is the event on which the denominator d is bounded from below. Is bounded below by this quantity. Okay? So indicator of En plus indicator of En complement. Okay? So on En complement, which is in principle difficult because then the denominator may be very small, I'm just going to say that this ratio, it's a mass, so it's smaller than 1. Okay? And then when I take the expectation on the theta naught, I just get the probability and the theta naught of the complement. Okay? So E theta naught of this, okay, is smaller than, so on En, on the other hand, I know that the denominator is bounded. Okay, so here I take the numerator, I keep the same, so E theta naught of it. And since the denominator is non-stochastic now, I can pull it outside the expectation. Okay, so I just replace the denominator by its lower bound, which is over there. So pi of b, e minus 2n epsilon n squared. Okay, so here I apply lemma 1 with epsilon equals to epsilon n and c equals to 1. Okay, good. All right, and I can drop this indicator plus, And on the complementary event, I just said that the ratio is smaller than 1. So here I just get p theta naught of En complement. And by lemma 1, this is a little o of 1, okay, by lemma 1. Okay, good. And now it suffices to control this. And maybe I can just do it over here. So I just do Fubini. Okay, so this ratio so actually I'm working on the indicator that p theta naught, I didn't write it, but is a non-zero. So I do Fubini. This is equal to integral over so an, okay, an of integral p theta over p theta naught of x. So indicator p theta naught positive, p theta naught of x d mu of x, and d pi, still have a d pi of theta. Okay, but here, since it's a probability, I just get integral p theta naught positive of p theta x d mu x, and this is smaller than 1. Okay, so this is smaller than pi of an. Okay, and that's it, because now this is smaller than pi of an, and by assumption this will go to 0 plus a little o1. Okay, so now I have this extra tool. Now we have it that if a sequence of sets has very small prior probability, the posterior mass of these sets is also very small. And combining these two results, we actually get now to the simplest version of the generic theorem. So due to Gozal-Gosh-van der Waart, so I will just a little bit informally call it either generic theorem or GGV theorem. Okay, so theorem 1.1. So GGV version with tests. So I'm going to take, again, epsilon n is going to be a sequence such that n epsilon n squared go to infinity. So by the way, there are also non-asymptotic versions of what I write, but so for simplicity, I'm taking mostly the asymptotic approach here, but you could also, here we use Chebyshev, for instance, so here we get some polynomial decrease, but by using some more refined, so if you make more assumptions, you can use more refined concentration equalities here to improve this, and you have all type of refinements there, which I'm not discussing here. But you can find them, for instance, in the very good book by Gozal and van der Waart, 2017, which is a very nice account on this rate theory. Okay, so suppose there exists so C a constant, theta n a sequence of measurable sets, and some tests. So what is a test? The test is just a measurable function of the observation that takes values in 0, 1. Okay, so test, it's like a statistic, but it takes values in 0, 1. So either 0, 1, so you just reply false or correct. You could also consider generalized test with the whole interval here, but it's enough to have discrete tests. Such that we have three conditions. So I'll write the most mysterious maybe first, and of course we'll discuss that in the sequel. So we are going to assume that these tests have a certain control of their type 1 and type 2 errors. So type 1 error is so with respect to the point theta naught So the expectation of the test is little O of 1. And now for the type 2 error, I'm going to assume that the supremum, so for all the alternatives in theta n that are far away from theta 0, so I'm giving myself a distance d on capital theta. Okay. So d is a distance on capital theta. So I'll come back to that also in a second, what type of distances we can consider. Larger than m epsilon n squared, m epsilon n of e theta 1 minus psi n. So that has to be smaller, so not only go to 0, but smaller than some exponential, like this. Exponential minus a constant c plus 4 n epsilon n squared. Okay? So second, that's the most complicated assumption. Then, and we'll have soon a version of this theorem with this assumption replaced by something a little bit simpler. So the complement of this theta n set has very small prior probabilities. So that may recall this lemma 2, where it means that I can drop this complement actually from the posterior if I control, at least if I control the prior of the Kullback-Leibler neighborhood, which is going to be the third assumption. So maybe the most important assumption in spirit is the last one, and it's saying that the prior mass of the Kullback-Leibler neighborhood is larger than some exponential minus c n epsilon squared. Okay? And so note that I chose the constants so that the constant for the pi of the n complement is a little bit bigger than the one for the Kullback-Leibler neighborhood, so that I can apply this lemma. Okay. Then, so if we have this, epsilon n is, so for m large enough, for large enough m, we have that e theta naught of pi, the set of thetas such that d theta theta naught larger than m epsilon n, given the data, that goes to 0 as n goes to infinity. Okay, so it means that m epsilon n for m a large enough constant is a convergence rate for the posterior distribution. Okay, so that's a certain testing condition. That's a condition we'll call on sieve sets. So if we view this theta n as sieve sets, and the last one is a prior mass condition. Okay, so I guess that conditions 2 and 3 are fairly intuitive given this lemma. And 1, except maybe for those of you who are a bit familiar with nonparametric testing, it may be, it's a bit, for now, it's hard to interpret. So in terms of nonparametric testing, it would say something that, like, you can test theta 0 against the complement. Sorry, there is theta 0 missing here. You can test theta 0 against a complement of a ball around theta 0 of radius epsilon n at an exponential rate. But what you would get generally in nonparametric testing is going to 0 here. And here you want actually more. So it means that this epsilon n may have to be different, slower from the usual nonparametric testing rate. Okay? But I mean, that's just, we don't need this interpretation. So in the remaining maybe 5-10 minutes, let me just, we are going to prove this, which is given what we have already, it's not very difficult. And then I'm just going to state a slightly different version with entropy instead of testing. Okay? So we can note that already that 2 plus 3, that implies that the complement of theta n as vanishing posterior mass. Okay, so it means that we can work on a set script Cn, which is, it suffices to prove the result on the set capital theta n. Okay. All right. So as before, so it's enough to consider the, okay, I can introduce the indicator, well, not the indicator here, the tests rather. The indicator will come in a second. So this is, I can write as E theta naught of pi Cn given x psi n plus the same but with 1 minus psi n. Okay, so just say that 1 is psi n plus 1 is psi n. Okay, and the first bit, since we know that, so the test takes value in 0, 1, it's smaller than, sorry, no, since this is a prior mass, it's smaller than 1, so this is smaller than E theta naught of psi n, which is a little o of 1. Okay, so it's enough to focus on this thing here. And so this thing here, I can write, I can just put the test inside the 1 minus psi. I will put, so it depends on x. Huh? So I will put inside the base formula. So integral of 1 minus psi n of x. So p theta over p theta naught x d pi on the set Cn d pi of theta divided by the integral over, so just the normalizing constant. Okay, so here I can just redo the same trick as before. I can just write again to bound the denominator from below. I can just write indicator En plus indicator En complement. Okay, and if I do that, I can really use the same argument as before. So I get smaller than, so I bound the denominator from below, so I get pi of b, of the Kullback-Leibler neighborhood, e to the minus 2n epsilon n squared. Okay, so that's the bound from below on the denominator. Okay, which was here. And okay, so I have this. So here I had maybe no, so it's a C here from the lemma. Okay, so what did I put? Sorry, just a second, so that I'm correct in the constants. Yes, so it's a 2, sorry. It's a 2 or it's a C? It's a C, but the C was 1, so it's a 2. Okay. Right. So I can bound this from below. Okay. So I have this, and E, so I take the expectation outside, E theta naught. Okay, so E theta naught of what? Of the integral over Cn of 1 minus psi n of x, p theta over p theta naught of x d pi theta, okay, and plus a little o of 1, which comes from this, I do the same reasoning as before. And now I just have to insert on the numerator, so I do Fubini here. And here I'm going to use the fact that E theta naught of 1 minus psi n of x, p theta over p theta naught of x is equal to, smaller than the integral of 1 minus psi n of x, p theta of x d mu x, which is exactly what is here, E theta of 1 minus psi, so on Cn. And this, by assumption, I can control it by, since it's on the set Cn, is by e to the minus C plus 4 n epsilon n squared. Okay? And now I can combine everything because pi of b now by assumption is bounded from below by this. And so since I have c plus 4, I have a plus 2 coming from here and a plus c coming from here. So I get that this is indeed smaller than e to the minus 2 n epsilon n squared. So I was even a bit generous here. So you get little o of 1. Okay? So it's really the same reasoning as for the proof of lemma 2, but you just insert the tests. Okay. So now I'll just, maybe in the next very few minutes, I'll just maybe state here a slightly more explicit version of this testing condition. So I'll give a different, well, maybe let me just give the second generic theorem, and I'll explain how we get to that. So theorem, so I think in the notes is 1.3. So now I have two rates, epsilon n bar up and epsilon bar down, with the minimum, so n squared going to infinity. And suppose I have a distance d distance on theta such that the following condition T holds. Okay. So this condition will just say that instead of testing a point versus a complement of a ball, I can test a point against a ball, which is something much simpler. So it says that there exists K and A, okay, such that for any epsilon and any theta 0, theta 1 in capital theta, such that the distance between theta 1 and theta 0 is larger than epsilon. Okay. There exist tests such that I control now the type 1 and type 2 error, so test phi n, in an exponentially decaying way. Okay, and the sup over theta such that distance of theta 1, so in a ball, if I'm in a ball here of radius a epsilon, so I have theta 0, which is apart from theta 1 by at least epsilon, and here I have a ball of radius a epsilon of e theta 1 minus phi n. So this is smaller, this quantity is smaller than e to the minus k n epsilon squared. Okay, so I have a new testing condition which is simpler, okay, which is just testing a point versus a ball. Okay, so suppose we have this, then, and no, I think I'll end on this because I'm just slightly over on time, so we'll continue from there tomorrow. So the first condition now is this testing point versus ball, which in general is relatively cheap to obtain. And if we have that, suppose further, so we are going to replace this first condition by an entropy condition. So suppose there exists C and D positive, and again these sieve sets such that So the first condition is now an entropy condition. So n is the minimal number of balls of radius epsilon n necessary to cover theta n for the distance d. And that I assume that I have some bound like this. And then the two other conditions are exactly the same as before with, so I can just copy them, e to the minus, so the only difference is I allow a different rate. So here, note that the rates had to be the same for the first and 2 and 3. Here, I allow possibly for a different rate, and at the end, I get the worst of the two. That's just, it gives a little bit more flexibility. You don't have to tune too much the constants. But it's essentially the same spirit as before. Okay, this is bounded from below by, so you have to match condition 2 and 3, C times C, okay? So I take the worst rate of the two. Epsilon n is the max of epsilon n lower bar and upper bar. And then for m large enough, you get the same condition. You get that epsilon n is a convergence rate for the posterior, which I'll sometimes actually write in so I don't write the set of all thetas, I just write to be quicker, just like this, given the data goes to 0. Okay? So this is the second version of the theorem where you replace, so you have sieve and prior mass, and you replace the testing condition by a simpler testing plus entropy. Okay, and it's not very difficult to prove once you have both. Okay, so I think we can stop here. Thank you.